Okay, so good afternoon, everyone. So this is the lab for week 9. And you see number 1 is essentially your assignment 2 and the first part of the project. So I'm not going to do question 1, but you can see that question 1 explained to you every step for you to do Euler methods for a function, for a system of ODEs, okay? So you see, y is a vector of d-dimensional. So in the project, d just equal 3. Okay. So the function f has d component as well. Say f1 up to fd. So in your project, d just equal 3. Yeah. So for example, in this example, d just equal 2. So you have only 2 equations. Yeah. Then you can write down the equation in the form of vector y prime equal vector f of ty, and the function f is given like this. So two components. The first component gives you the first ODEs. Okay, so you relabel x to be z1 and y to be z2. Okay, so z is a vector. So then, you know, your initial condition is a vector as well. So y0 here, it's just x0 is 4 and y0 is 5/4. Okay. And so now when you discretize the domain, yeah, then you chop it into equally spaced intervals. You chop it into capital N subintervals. Okay, so Tn is just given by this formula. And then when you try to solve the Euler method, when you apply the Euler methods, so remember the yn plus 1 here, okay, is the numerical solution at time tn plus 1. So it's a row vector. So it's a row vector like this. Okay, sorry, it's a column vectors like this. So in the project, you know, you have 3 equations. So just y1, y2, y3, and that's it. But then when you solve the ODEs, so remember you march in the time forwards. So initially you have T0 and then T1, T2, up to capital Tn. Your solution will be a matrix. Okay, so your solution is a matrix. So what is the meaning of the matrix? So the matrix is the very first row give you the numerical solution of the first ODEs in the system. In the second one, give you the solution for the second ODEs, and so on. So you see, so that's why your solution is a matrix. And in order to plot one solution, you have to take out one row of the matrix and you plot it. Okay, so I'm not going to do Euler method, but I'm going to do Runge-Kutta method, and you will see the same idea apply. So Runge-Kutta method of order 2 is given by those tables. So first we have to write down, you know, what is the formula corresponding to those 3 tables. So maybe we do the first 2 tables, and then you can see those MATLAB function in Moodle. Yeah, so RK2A, RK2B is in Moodle in the lab directory. So now let me show you from this table, how do we get out the formula? So let me take a piece of paper and show you how to get the paper. Okay, so now the very first table is 0, 1/2, and there's a 1/2 here and a 0, 1 here. So this one is C1, this one is C2, This one is B1, this one is B2. So if you compare with the lecture notes, remember there is a table and this is a vector C and there's a vector B, okay? And this number is A21, okay? So then how do we write down the formula? So the formula will be given by xi1 equal yn and xi2 equal yn plus, okay? So now we have to take A21. We have to take A21 and multiply by h. So you got h over 2 f of Tn xi1. Okay. So f of T1 xi1, yeah. And then what is yn plus 1? So yn plus 1 will be you take B1 here. Well, first you have to write yn first. And because B1 equals 0, so I don't write anything. Then I got B2 multiplied by h. So B2 give me this one. And then f of, so B2 corresponding with Tn xi2. Okay. And then remember, because you have to xi2, you have to add C2h. So you have to add h over 2 here. Okay, so this one comes from the C2 here. So this one gives you the formula for the first table. And you can do the same for the second table. You know, but now, so maybe we do it for the second table and then we do with the third table. So here we have a table look like this. So 0 to third, 1 quarter, 3 quarter. Okay. And you know, you do the same. So xi1 will be yn, xi2 will be yn plus. And now you have to take out this number. Yeah, so take out this number, A21. So A21, because it's a matrix, 2 by 2 matrix. This is a row 2, column 1. So 2h over 3 f Tn xi1. And then you have yn plus 1 will be yn plus. Okay, so now because we have B1 is non-zero, so you got h over 4 f of Tn xi1, okay, plus 3h over 4. So the 3 quarter come here, 3 over 4 come here, yeah. F of Tn plus, okay, so do not forget the C2. So 2h over 3 xi2. Okay, and so those two methods have been implemented already. So this one is RK2A and RK2B. So we will look into those files. Okay, and now we work on the formula for the third table as well, because we will use it to implement the RK2C. So now if you have a table, the third table, yeah. So third table look like this. So the third table is 0, 1, 1, 1/2, 1/2. Okay, so then you got xi1 is just yn, xi2 is just yn, and now because there's a 1 here, so plus h f of Tn xi1. Okay, and then similarly you have yn plus 1 equal yn plus h over 2. So this is h over 2 come from here, yeah. F of Tn xi1 plus h over 2 f of Tn. So now do not forget to add C2 here. So C2 is so this one is C1, C2 just 1. So you have to add H xi2. Okay. So now we work out all the formulas. Now we look into the MATLAB. Okay. So now if I just save those formulas, and now I go back to MATLAB. So now you see that my RK2A look like this. Question? How do you know many terms you have for the expression? Good point. Yeah, so that is a very good question. So that's why you have to look into the table, right? So the table gives you that many terms, yeah? So you see so if I go back to the piece of paper, yeah? Well, the very first table is a special case because B1 is just equal 0. So therefore, you know, the B1, the first term drop out. But then it's 1, so I put in the term here. So, but it should have 2 terms, okay? Because the tables has 2 rows, yeah? So then it should have 2 terms. And the second tables and the third tables, each of them have 2 terms, you see, for the yn plus 1. Okay, and so everything is okay, yeah. The number of B, yes, essentially the number of non-zero entries, okay, because sometimes if it's 0, then you just drop it, yeah. Okay, so now we go back to the MATLAB again. So now you see RK2A look like this, yeah. So this is the formula on the piece of paper, right? So you got xi1 yn, xi2 is yn plus hf tn xi1 over 2, and yn plus 1 is just yn plus hf tn plus h over 2 xi2. Okay, so those coefficients are given. And remember, where do we get those coefficients? Well, we have to solve nonlinear equations come from the Taylor expansion, which is complicated. So at the end of the day, we just need those numbers to implement the method. Okay, and you can see that you just translate those formula directly into MATLAB. Yeah, so the only thing different in this formula and MATLAB is you have this one. So what does it mean? It means that, you know, I mean, now at time Tn, it's a vector, it's a column vectors, because this one, you know, you can solve for D ODEs at the same time. Remember, you can do it for 2 or 3 ODEs or any numbers of ODEs at the same time. So that's why we put in this one. So this one just means that every columns, okay? I mean, at the end, you just take a column vectors and you just apply the formula, okay? So now you can see the same for RK2B, okay? So in this one, we wrote down the formulas on the piece of paper before, and this one is just the same, yeah? Well, except that you have h over 4 common factors, and then you have number 3 here. But anyway, just the same, yeah? And then you see you translate it into the MATLAB commands, okay? So now the question is, how do we use RK2A? Okay, so now we have to make a new script to test RK2A. Okay, or 2B, yeah. So RK2 means that run scatter method order 2, A version A. Okay, so now we are going to use the function. We are going to use the ODE given in the problem. So in the problem 2. So now if you go back to the question. Okay, so I'm going to use, you know, like RK2A to solve the question 2I and 2.6. Yeah, so 2I is just this ODE, and 2.6 is just a system of two ODEs. Okay, to see how it works. Yeah, so the first is only one ODEs. So let me copy it down into MATLAB. So I stop this and I print back MATLAB again. And then now what is the ODE? So the ODE will be y prime is t e to the 3t minus 2y. Okay, and now t is between 0 and 1. And y0 is just equals 0. So the initial condition is just equal 0. So first, I just define my function f, what is the right-hand side of the ODEs. So in general, it's a function of time and of y, right, of the ODE. Yeah, so it will be t time exp 3t. And because you might want to plot it, so make it a vector friendly minus 2y. Okay, and then the left hand side is just 0, right hand side is just 1. So y0 initial condition is just equals 0, and the number of time step, so maybe the number of subintervals, say 10. Okay, and now I'm going to, well, in this case I know the exact solution, so by calculus, so y exact is the e to the 3t divided by 5 minus, so I just copy from the problem, so divided by 25 plus e to the 2t divided by 25. Okay, and now you just call the RK4 function, right? So remember not RK4, RK2A, yeah. So remember, how do you call it? Well, okay, so I'll give you the hints. Okay, so F string, what is F? A, B, Y0, N. Okay, and now you want to plot it. Okay, so now how do I plot it? So plot, so remember the length of the vector t is only 10. Okay, but you want a final plot, so maybe I take the plot to be a line space from A to B with 1,000 points. Yeah, so I have a final resolution, and then I will plot the exact solution. Yeah, so t plot with y exact of t plot. Okay, and then I'm going to plot the numerical solution. So this one I want to plot, it's a blue curve. Yes, a blue curve, and then this one is like so ty is a numerical solution. So this one is a red star, for example. Okay, so red star, and now I run it, see whether it works. So I have to give a name. So test RK2A. Okay. Well, it doesn't work. Yeah. So let's say that. Okay, because I haven't defined a variable for y exact, so it has to be even like anonymous function. Yeah. Okay. Now run it again. So I can show you the plot. So stop this. I'll share you the plot. So you can see that the red star are the numerical solution. Okay. And the blue curve is the exact solution. And it agrees very well. Okay. So we did it. Okay. And now the next step is how I'm going to use RK2A to solve a system of ODE. Okay, so line the question. So now I'm going to make a new script. Yeah, so maybe I just cut and paste from here first. Yeah, so cut and paste. So we want to save some time, so we cut and paste. So this one is when you call the ODEs. We need to modify it first. Yeah, but now, so remember the ODEs is a system of two equations. So now let me, well, maybe you remember the question already, but I need to write down. Yeah, so I need to write down the equation, so then I remember. So now the equation will be so you got dx dt, maybe x prime, yeah, equal xt plus 4 yt e to the t. Okay, and x0 is equal 4, and then y prime equal xt plus yt plus 2 e to the t. Okay, and so y0, the initial condition is 5/4, right? 5/4. So now I need to define the ODEs. Yeah, so I need to define the capital function f. So f will be a function of t, well, maybe we use a new variable called z. Okay, so if you read, you will see that. Okay, so you read the question 1 already, so you remember that you can define z1 to be x and z2, the second component of z, is y. Okay, so z, remember z now is a vector, so z is a vector with two components. And now f return two component as well, x1 and f1 and f2. So maybe separate by 2 lines. Yeah. So the first line will give you the first ODE. So x will be z1 plus 4 z2 minus e to the t. Yeah. And now what is the second equation? So the second equation will be, you see the same pattern here. So z1 plus z2, what is for y, plus 2 times e to the t. Yeah. Okay, so now you can define the exact equation this way as well. So remember there's exact solution. So exact solution, so y exact maybe Z exact, yeah, because we use for X and Y already. So Z exact is, so remember Z exact is X exact, and it's given like this. So this one from calculus, and I just copy from the question. So E xp to the minus t minus 2 to the t, yeah. And then the second equation will be 2 exp 3t minus e to the minus t plus e to the t divided by 4. Okay, I want to plot the exact solution as well. And remember, because this function depends on t only, so you can define this anonymous function. Well, take in only one variable t, but it gives two outputs, yeah, I mean two rows of output. The first one is a function x, and the second one is a function y, yeah. Okay, so now I'm going to use RK2A. Okay, but now what is the initial condition? So what is the initial condition now? So what is the initial condition? Anyone? What is the initial condition now? So how do I define the initial condition? So how do I define the initial condition? Okay, so yes, 5/4, yeah. So 5/4, but remember, you know, I mean, make sure that you have to give it the column vectors, okay? So according to the description in question 1, says a column vector, yeah. So y0 is just x0, y0, yeah. Well, strictly speaking, you can say that this one is z0. Okay, so maybe because we should be consistent with the notation. So this one is z0, and this one is z0, and then you compute z. Okay, so then well, now how do we plot? How do we plot the solution? So now we can run it. Yeah, so suppose you get out the solution already. Now how do we plot it? So first, you know, like before, you can define a final vector t, right? Because remember, this vector t is only 10 points. Yeah, you choose only 10 subintervals. Okay, 10 or 11 points. Yeah, but this t plot can be 1,000 points. Yeah, and then you want to plot two solutions separately. Yeah, so you can plot. So now how do we get out the solution? Well, so t plot. So first, okay, so first we have to get our z exact first, yeah. So z exact of t plot, yeah. So this one is, I call it z plot. So z plot is the z exact applied to t plot, and this one is 2 by 1,000 matrix, right? Because remember, you know, like every t, it gives out a column vectors, yeah. So then this one is 2 rows, and each rows contain 1,000 columns. Each row contain 1,000 entries, yeah. So now you plot you plot T plot, okay, Z plot. Maybe let me define another variable to make it clearer. Yeah. So I call it like X plot, okay, to be Z plot, the first row. The first row. So the first row, yeah. So this one give you the X plot of the exact solution. Yeah. So this one exact X T, yeah. And then you give Y plot is Z plot, but the second row, yeah. So this one is exact YT. Okay. So now you can make two figures, or you can plot everything on the same figures. It's up to you. But suppose I plot two figures separately. Okay. So suppose two figures, yeah. So the first is two figures. Then first I plot T plot and X plot, and then T and Z1, yeah. Well, so maybe essentially this one, they just give you the first solution, yeah. So this one is a blue curve again for that exact one, and this one is the red star for the numerical, okay. And then you can do the same for another solution, yeah. And then you make two separate figures. So then, you know, this one give you a new figure. So this one give you Y plot, and this one the second row, yeah. So remember Z is 2 by n. So Z is 2 by n matrix. Okay. And now we run it. So see what happened. Yeah. So we run it. So test RK 2A 2D. Okay. So there is something wrong here. So Z plot. Okay. So we use the variable incorrectly. Okay. So run it again. Okay, so now I can show you my screen, yeah? So then you will see that the two figures are right here. So let me make a share the screen. So let me stop this, share my screen. See, so you can see the two plots, yeah? Or you can combine two figures into one. Okay, so you can combine two figures into one. So if you want to, so suppose I plot I close this, yeah. And suppose I plot the one single figures, yeah. So suppose this one is two figures, and if I want to plot one figures, then I just use, I just combine all the elements here. So because the plot command, it just take a pairs, yeah, and it plot the pair for you, yeah. But the pair should have the same length. Okay, so now suppose I plot it, and here you will see that. See, so now you see that two solution X and Y on the same plot. Okay, you can change the color as well. can make a title, so on and so forth. Okay, but we haven't so stop this. Yeah, so we haven't implement the third method yet. So let me go back to the RK2A. Yeah, so RK2A. So now what we want, maybe RK2B. Yeah, so what we want is we want to modify this to implement the third table. So now if I save as RK2C, okay. So this is, I need to change this, yeah. So now if you remember my previous calculation on the piece of paper, now I just copy down the constant. So C is 0 and 1. Okay, and then you have B is just 1/2, and this one is just 1, 0. Okay, and now the iteration is given by yn, and this one only h. Okay, and then yn plus 1. So this one is h over 2, and combine the two terms. So we worked it out before already. Yeah. So now I just copy down the coefficient. So now there is no number 3 here. And this one is only h. Okay. And now we need to modify the MATLAB to reflect the changes. Yeah. So now this one 2/3 just become only 1. So 1h. Okay. And this one is h over 2. Okay, and this one is xi1. So xi1, and this one is xi2. Oh, this one only h. Okay, and this one only, you add the two terms. Okay, and now we just save and run it. So we go back to the test of the single ODE. Yeah, and now you replace this one by another line, and we call it RK2C. Okay, sorry, 2C. Okay, so we run it. So we save it and we run it. And you see, I can share to you the figures. So the figures will be very close to what we had before. So I stop this and I show you the figures. Okay. And you can do the same for the 2D. So suppose I go to the 2D case. So the system of two equations. So now I'm going to change this into RK2C. Yeah. I will change this to RK2C. Yeah. So RK2C. And now I run it. Oh, so there is some problem. So there is an errors in RK2C. Okay. So this one we forgot to put column vectors. Yeah. Okay. So now I think it will run. Yeah. So now go back, run it. So I can show you that the figure look like this. Okay. So this is the X and this is the Y. Or we didn't put the legend, but you can do it later, yeah. So now the next question is we are going to do RK4. Okay, so you got we got something like this already, yeah. So now what I want to do is I want to do RK4. Okay, so RK4, then first we have to write down what is the formula for RK4. So by this table, so now get our piece of paper again. So where is the where is my camera? No, not this one. Share the camera, yeah. Okay, so now we go back to the piece of paper because we need to write down the formula correctly. Okay, so now if I have the table with me, yeah. So the table is 0, 1/2, 1/2, and 1. So you can see that it's 1/2. I put the table away. So 0, 1/2, 0, 0, 1. And this one is 1/6. 2/6 is 1/3, 1/3, and 1/6. Okay, so this one, you see that it has four rows, yeah? So you have to have, so the number of stages is 4. So nu equal 4. Okay, so you have to have xi1 equal, xi2 equal, xi3 equal, xi4 equal. And then you have yn plus 1 is yn plus 4 terms, yeah? So, so we do it step by step, yeah? So xi1 is always equal yn for explicit Ron's-Cotter method. And xi2 is yn plus, okay, so now we have to collect this coefficient, yeah? And we put it here. So it will be h/2 f of Tn xi1. So this one is C1, C2, C3, C4. This one B1, B2, B3, B4. Okay. So xi3 will be yn plus. Okay, so now there's nothing with respect to xi1. There's a 0 here. So I skip this. Then there's something with respect to xi2. So I have to put in h/2 f of Tn. Okay, so now we have to be careful because it's xi2, yeah? So xi2, you have to add C2H, yeah? So you have to add h/2 here. And then xi4 will be yn. And there's nothing for xi1, nothing for xi2, but there's a thing for xi3. So it will be hf Tn plus xi3, yeah? And now you got C3, so C3 is 1/2, so you got h/2. So then this one gives you xi1 up to xi4. And now we need to write down what is yn plus 1. So 1 plus 1 is yn plus b1, okay? So b1h, so h/6 f of Tn xi1, okay? And then plus h/3 f of Tn plus, so remember this is xi2, so xi2 you have to add h/2 xi2 and then plus h/3 f Tn plus h over 2 xi 3. And the last term, the very last term is from before. So h over 6 f Tn plus, okay, so do not forget the C4 equal 1. So h xi 4. Okay, so now once you got the formula, you just implement it in MATLAB, translate it into MATLAB, and you got the RK4 method. Okay, so now I put this formula into MATLAB and I solve it again. So now let me put everything into MATLAB. So now suppose I have RK4C. Okay, so let me save as, or maybe I make a new one called RK4, yeah. So, but I will cut and paste from this. Okay, so we rename it RK4. Okay, so with, well, see, so now we have to modify this table, yeah. So now xi1, so now if I have my piece of paper here, yeah, so I assume that I have a piece of paper, I write down the formula. Now I just got h over 2 here. Okay, and then I have to have xi3 is yn plus h over 2 f Tn xi2. Okay, and do not forget to put in h over 2 here, and then you got xi4 is yn plus h f Tn plus h over 2, and then you got this one is xi3. Okay, and now so we just have to multiply by h, yeah, for the whole thing, yeah. So you got xi1, so this one is xi1 already, so 1 over 6, 1 over question. Yes, this is a group assignment question. Yes, but you see, I mean, the implicit one is more complicated. So I assume that everyone will get this. This one is an explicit one. Okay, so the explicit one. So this is a group assignment question for explicit logical method of order 4. Okay. And if you look into Moodle, you see that I put the RK4 for the one-dimensional already there. Yeah. So now h over 6, yeah. So h over 6 time f yn. So this one is h over 3 Tn plus h over 2 xi2 plus h over 3 f of Tn plus h over 2 xi3 plus h over 6 f of Tn plus h xi4. Okay, so now you just need to implement this formula into MATLAB. Okay, so this one is just h over 2 and then xi3 will be So essentially exactly the formula, right? So h over 2 xi 2. So this one xi 2, and then you have to add h over 2 here. Okay. And then you got xi 4 as well. So xi 4 will be yn plus h times so tn plus h over 2 xi 3. Yeah. So once you got the formula correctly, then you just plug it in. Yeah. So now, so this one will be h over 6 multiply with, so you can take h over 6 to be the common factors. Then this one will be so the second one will be 2. Yeah, 2 over 6 is 1 over 3, and this one is h over 2, and then you have to add 2 more terms. Yeah, so you have to add 2 more terms. So the term for xi 3, the term for xi 3, yeah. And then there's the last term is for xi 4. So the last term is for xi 4. So make sure that you have to put in the formula correctly, otherwise it's not going to work, okay? So xi 4, and the last one is just like this. And you save it, okay? And the name is RK4, obviously, yeah. And then now you can go back to say test RK2A. Okay, and now you replace this one by RK4. And see whether it works or not. So now suppose I run it. Yeah, so it give me the correct. So I stop this and okay, so you see, so it give me the correct solution. So I agree very well. Yeah. And you can try it with a system as well. So suppose I'm going to go to the system of 2 ODEs. Yeah. So I replace by RK4. Okay. Save it, yeah. So then you run it, and then I can show you the output. So okay, so the output is like this, yeah. So I agree very well with the exact solution. So you see that, you know, I mean, for the project, you have to do exactly the same. Well, I mean, plus you have to derive the errors table and the order of conversion. Okay, but that is more or less the